Good morning. This presentation introduces the research title Improving Sentiment Analysis of Ukrainian Language Content by Applying a Rule-Based Approach, conducted as a part of Collins 2025. The study originates from Lviv Polytechnic National University. It addresses the critical need for accurate sentiment analysis in languages that differ structurally and culturally from English. This area of research is essential as Ukrainian content grows rapidly online and there is increasing demand for localized NLP tools. Rule-based approaches, while often overshadowed by deep learning, can provide better linguistic transparency and control for specific language domain. Sentiment analysis is a core task in natural language processing, used to classify opinions expressed in text as positive, negative, or neutral. This technology supports applications in journalism, business, and public policy. However, most sentiment models are built for English, which poses a problem when analyzing text in Slavic languages like Ukrainian. Challenges include inflectional variation, synthetic flexibility, and domain-specific expressions. This research proposes a solution using a rule-based approach that can operate reliably without requiring large labeled datasets. Current tools like Vader and TextBlock rely heavily on English-centric resources. Although transformers like Euchre Roberta and mbert support multilingual inputs, they're difficult to interpret and lack handcrafted linguistic control. Many academic publications now highlight the trade-off between model accuracy and explainability. This project positions itself within a growing movement for interpretable, resource-available natural language processing, particularly in underrepresented languages. This remains limited literature specifically on Ukrainian sentiment classification using rule-based methods. The primary purpose of this research is to develop a sentiment analysis system specifically optimized for Ukrainian language. This involves constructing a modular pipeline that integrates linguistic features, lexicons, and parsing strategies. Key tasks include building and refining a custom sentiment lexicon, including emotional polarity and part-of-speech data, incorporating emoji sentiment and contextual phrases, implementing a dependency parser to extract synthetic patterns, and conducting comparative experiments with Wader using real-world data. Each task was designed to address an existing gap in current sentiment models. For instance, generic models often misclassify negations or fail to interpret modifiers correctly. In Ukrainian, expressions such as "не дуже добре" carry complex sentiment signals. The inclusion of phrase-level sentiment and synthetic weighting was critical for improving both precision and recall. This work also provides a foundation for similar projects in related languages. The proposed system successfully integrates rule-based logic with linguistic resources. The architecture is modular, consisting of preprocessing, lexicon mapping, and scoring components. Lexical data are enriched with manually created polarity scores, emoji interpretation, and idiomatic phrases using dictionaries. Parsing rules account for booster, reducer patterns, and punctuation intensity. This diagram illustrates the complete data flow from raw input to sentiment classification. Let's dive deeper. The lexicon was built using the MLX framework, which provides emotional and polarity values for thousands of words. The Ukrainian version was expanded to include colloquial expressions, domain-specific phrases, and multi-word units. Emoji sentiment was integrated based on prior research mapping emoticons to positive, negative, or neutral labels. Entries were annotated manually to reflect the real-world usage on platforms such as Twitter or Telegram. Text preprocessing. Preprocessing begins with tokenization, preserving casing, punctuation, and emoji characters. A part-of-speech tagger and lemmatizer are applied to standardized forms. Stop words are removed and relevant tokens are passed to the sentiment engine. N-gram extraction supports the detection of idioms and sentiment-bearing collocations. This preprocessing stage ensures consistent input structure for scoring. As you can see on the figure, the decomposed process of text preprocessing. The analysis phase identifies syntactic dependencies such as subject-verb and modifier-target relations. This allows the system to apply rules for negations, example, нещасливий, not happy, and intensity adjustments. Exclamatory punctuation boosts scores, while ellipses lower confidence, triple does. The sentiment score is updated dynamically through these adjustments, producing a weighted outcome. Such rule combinations improve the nuance of classification over keywords-only system. And as the final score combines all elements, token polarity, dependency roles, punctuation markers, and modifier weights. The system assigns a compound score in the range of -1 to 1 and labels the text as positive, neutral, or negative. This three-class output is consistent with standard sentiment analysis frameworks. A key advantage of this system is its transparency. Every step from input to decision is traceable and modifiable. Let's talk about Wader for a bit. Wader, while efficient and popular, was designed for English and fails to capture the structure of Ukrainian language. In this study, Wader required input to be translated before classification, introducing noise. The proposed system avoids this issue by operating directly on native text. Additionally, the new tool offers explainability, which Wader lacks. This side-by-side interface demonstrates how results differ in real use cases. And let's talk about results. Uh, Dobry and Pohany, good and bad. Two high-frequency sentiment words were selected for testing. Dobre and Pohany. The rule-based system classified 83% of Dobre cases as positive compared to 58% for Wader. For Pohany, or bad, results were 78% and 61% respectively. These findings confirm the system's improved sentiment sensitivity. The charts illustrate the classification distribution across the dataset. Overall, the rule-based algorithm delivered a higher accuracy and more meaningful score distributions. It responded correctly to negations, modifiers, and punctuation, unlike Vader. This advantage is especially important for sensitive domains such as mental health, education, or policy monitoring. Results also confirm the value of designing sentiment systems around linguistic structures rather than solely relying on statistical inference. And to conclude, language-specific rule-based sentiment analysis systems for Ukrainian has been successfully developed. It addresses limitations in existing tools by including native, grammatical, and emotional features. The system offers not only better accuracy, but also transparency, making it suitable for both academic and applied use. And let's talk about the future. Next steps include hybridization with deep learning models, automatic lexicon enrichment, and expansion to other Slavic languages. Incorporating real-time adaptation mechanisms and additional emotional dimensions such as joy, anger, or fear is also planned. Benchmarking against advanced models like GPT-4 or multilingual BERT will help validate its broader applicability. We're moving into AI era. Nothing we can do about it. Thanks for listening. Uh, thanks.